Hello friends, welcome to the next lecture of refrigeration system under the edges of chemical process utilities. Now in this particular lecture we are going to discuss about the refrigeration system components and refrigeration cycle. So before we go into the detail of this particular content, let's have a brief outlook that what we discussed in the previous lecture. In the previous lecture, we discussed about the various type of components like condenser, evaporators, we discussed about the throttling devices and auxiliary devices. This includes the accumulator, receivers, oil separators, stainers, solenoid valves, dryers, check valves, defrost controllers. And then we had a discussion about the vapor compression refrigeration system. Now in this particular lecture, we are going to cover the vapor compression refrigeration cycle with respect to the energy analysis and exergy analysis, and we'll give about the practical approach of vapor compression refrigeration cycle. Apart from this, we will discuss about the multi-stage refrigeration system. So when we talk about the energy analysis of a vapor compression refrigeration system, now it can be analyzed by applying steady state flow according to the first law of thermodynamics. Now you see that everywhere when we talk about the refrigeration aspect, we cannot overrule the importance of the laws of thermodynamics. And usually all the cycles, they are usually governed by the law of thermodynamics. So the first law of thermodynamics, you see that as applied to each of the four component individually. So if you recall the vapor compression cycle, all the steps like compression, expansion, evaporation, all these steps. So the law of thermodynamics, it's always applied to the all stages of this vapor compression refrigeration system. Now there is a energy conservation by each component and the entire system. Therefore, the energy balance equation for each component of the system becomes you can say very important. Now with the assumption that the kinetic and potential energies are negligible. So you can say that we are taking all these reversibilities into consideration and we need to take the proper assumption. Now here you see that these are the four integral part of your vapor compression refrigeration system, which we have already discussed, that the evaporator, which is maintained at that particular temperature, then the compressor, then condenser, and then expansion valve. And if we try to draw this particular steps into the TS diagram, here you see that this is the compression, isentropic, and then isenthalpic operation, as well as, so all these stages are depicted in this particular TS diagram. Now if we see that the compression, this starts at point number 1 here as a saturated vapor, and shaft work is added to increase the temperature and pressure. This is also known as the isentropic operation or isentropic process. And you can see that this is represented as a straight line in the TS diagram. Now this is superheating the vapor to the point number 2, that is this one. So obviously at this juncture we need to write the energy balance equation, and that is this energy balance equation is mH1 plus W is equal to mH2. Now where m is the mass flow rate, this one is the mass flow rate of a refrigerant, and usually it is represented as the unit is kilogram per second, and H is the enthalpy and having the unit of kilojoule per kilogram, and W is the compressor work rate and represented as kilowatt. So this is the W. Now if we talk about the condenser, you see here we are having the condenser. The process is the heat rejection process, and that is referred as QH. Now heat is removed from the system. So obviously when heat removal or addition take place, then again we need to write the energy balance equation. So the energy balance equation can be written as MH2 is equal to MH3 plus QH. Now here the QH is the heat of refrigeration from the condenser to the high temperature environment. Now next stage, that is from 3 to 4, and that is called the expansion stage. So if we talk about the expansion valve is attributed to the throttling process, and that is sometimes referred as isenthalpic process or the constant enthalpy process. This throttling process reduces the refrigerant pressure from the condensation pressure, this is very high, and for the evaporation pressure, and that is low. So the energy balance equation, that this can become the MH3 is equal to MH4, and as H3 is equal to H4, because it is an isenthalpic operation. So if we write the energy balance equation for evaporator side, it becomes MH4 plus QL is equal to MH1. So in evaporator, again heat is absorbed to the refrigerant from point 4 to point 1 or station 1 to station 1. The energy balance equation will become MH4 plus QL is equal to MH1. Now here this QL is the heat taken from the low temperature environment to the evaporator. So for entire refrigeration system, the energy balance can be written as W. W is the work done, because you are externally supplying this quantum of work, plus QL is equal to QH. Then we need to calculate the coefficient of performance. So the coefficient of performance, and sometimes referred as COP of the refrigeration system, it becomes COP is equal to QL over W. So the maximum COP, that is the coefficient of performance, based on the Carnot refrigeration cycle, it is given as COP is equal to TL over TH minus TL, and it is equal to 1 over TH over TL minus 1. The coefficient of performance or COP of the refrigeration system is always greater than 1, and that is the system produces more energy than the work input. So you can say that QL is greater than W. The practical refrigeration system are not as efficient as ideal models like Carnot cycle, because of the lower coefficient of performance due to irreversibility in the system. A smaller temperature difference between the sink and source, it provides a greater refrigeration system efficiency. So we discussed this particular theory in detail. Now it's time to have one question or one numerical question. Now the question is that, let us consider a refrigerator operates on ideal refrigeration cycle as per this figure. Now if evaporator temperature is minus 20 degrees Celsius and the condenser temperature is 40 degrees Celsius, and the flow rate in the cycle is 0.2 kilogram per second, then you need to calculate the compressor work rate, that is W, the condenser heat rate, that is QH, evaporator heat rate, that is QL, and the coefficient of performance. Now COP based on Carnot cycle, this need to be addressed. For convenience, we have given some useful data for the calculation purpose, like different numbers 1, 2, 3, 4, enthalpy in kilojoule per kilogram, the pressure in kilopascal, and the temperature in degrees Celsius. So as you know that for refrigeration cycle we need to have 4 different stages. So for every stage we have given this statistical data or the data required, that is for stage 1, the enthalpy is 386.08, for stage 2 that is 431.24 kilojoule per kilogram, and stage 3 and stage 4, these are the isenthalpic operation, and that's why the enthalpy is constant, and that is 256.54 for each stage. Similarly, if we are considering this the pressure perspective, so the stage 2 and stage 3, they are isobaric. In that case, so the stage 1 is having the pressure of 133.7, and stage 2 and stage 3, that is P2 and P3, they are equal, and they are 1017 each in the kilopascal unit, and stage 4 is having 133.7. So stage 1 and 4, they are isobaric. The temperature is stage 1 and stage 4, they are having the constant temperature minus 20 degrees Celsius, and stage 2 and 3, they are having 50 and 40 degrees Celsius respectively. So let's solve this particular problem. Now here, this is the compressor work. So if we take from station 1 to 2, so W is equal to M H2 minus H1, that is equation number 1. Now if we put on putting the values in the equation from the table, W is equal to 0.2 into 431.24 minus 386.08 kilojoule per kilogram. So if we calculate, it comes out to be 9.0 kilowatt. So work rate is 9.0 kilowatt. Now if that is from stage 1 to stage 2. Now for the condenser heat rate, and that is stage 2 to 3, we can write QH is equal to M H2 minus H3. So 0.2, which is given in the problem, into 431.24 minus 256.54. So QH comes out to be 34.9 kilowatt. Next stage is for evaporator heat rate. That is 4 to station 1 to station 4 to station 1. So this is QL is equal to M H1 minus H4. So it is 0.2 into 386.08 minus 256.54, and that is comes out to be 25.9 kilowatt. So the next stage is to calculate the coefficient of performance. So as you know that the coefficient of performance COP, that is QL over W. So if we write, this is, we have already calculated, that is comes out, that was 25.9 divided by 9, and it is 2.87. So for COP based on Carnot cycle, so COP Carnot is equal to TL upon TH minus TL, and that is 273.15 minus 20 upon 40 minus and minus 20. So the COP Carnot is 4.22. Now this is the maximum COP which we can achieve. Now let us talk about the exergy analysis of vapor compression refrigeration system. Now for exergy analysis, we have to write exergy balance equation for each component of the refrigeration system and for the piping as well. Now here you see that again we are coming back to our vapor compression refrigeration system. Again the compressor, condenser, expansion valve and evaporator, all these things are here. Now see, when we perform the exergy analysis of vapor compression refrigeration system, here you see that we have already mentioned that a simple vapor compression refrigeration system generally consists of 4 major operations. One is the compression, that is attributed by the compressor, condensation, that is with respect to the condenser, expansion through the expansion valve and evaporation through the evaporator. Now the working substance is a refrigerant. Now in piping from 1 to 2, the refrigerant generally experiences a pressure drop and heat gain from the environment. So in the compression process of from station 2 to station 3, the mechanical work is supplied and converted into the thermal energy. So at the compressor discharge, the substance is at high pressure and its flow availability, that is exergy, is increased. Now if we go to station 3 to 4, the substance passes through the condenser. This is the condenser. Now condenser and leaves as saturated or subcooled liquid. Now in condensing process, heat is transferred away or extracted away from the refrigeration system. The pressure drop across the condenser because of the friction. Now if we go from station 4 to station 5, when the substance goes through the expansion valve, it experiences a substantial pressure reduction while its enthalpy remain unchanged. So when we talk about the final system, that is from station 5 to station 1, it takes place in evaporator and the refrigerant receives heat from an external source and is changed back into vapor at either a saturated or slightly superheated state. So this reflects with respect to this TS diagram. Now the term I accounts for the time rate of exergy destruction due to irreversibilities within the system and is related to the rate of net entropy or entropy production. So the exergy balance equation for the component of the system, this becomes for piping between station 1 to 2, that it is delta E F 1 to 2 and it is minus I 1 to 2. Now where delta E F 1 to 2 is equal to M E F2 minus E and I12, that is M T naught into S2 minus S1 minus H2 minus H2 upon T naught. Now here this delta F1 to 2 is the change in the flow exergy rate and it is having the unit of kilowatt, and I1 to 2 is the irreversibility rate from station 1 to 2. Again it is having the unit of kilowatt, and Sgen is the entropy generation rate and that is kilowatt per Kelvin, and EF is the specific flow. F stands for flow. So EF is the specific flow exergy at the inlet and exit under the consideration, and the unit of this EF is kilojoule per kilogram, and T naught G is the surrounding or reference temperature and that is again having the unit of Kelvin. Now let us talk about the compression from stage 2 to 3. Now the exergy balance equation we can write as delta E F 2 to 3, that is equal to W minus I2 to 3, where delta F1 to 2 is equal to M E F 3, that is station 3 minus EF2, and I2 to 3 is equal to m T naught into S3 minus S2, and W is equal to m H3 minus H2. Now, if we take the condenser aspect from station 3 to 4, the exergy balance equation is represented as delta E F 3 to 4 is equal to minus I 3 to 4. Now, where delta E F3 is equal to m into EF4 minus EF3, and I 3 to 4 is equal to mt naught into S4 minus S3, that is S4 minus S3 entropy at station 4 minus entropy at station 3, plus enthalpy at station 3 minus H4, that is enthalpy at station 4 upon TH. Now, if we talk about for the condenser between 4 to 5, the exergy balance equation, it will be delta F 4 to 5 is equal to minus I 4 to 5, where delta E F 4 to 5 is equal to m E F at the station 5 minus E F at station 4, and I 4 to 5 is T naught S gen, and that is equal to m T naught S5, that is entropy at station 5 minus entropy at station 4. So, these are the equations. Now, if we talk about the evaporator side, that is station 5 to 1, the exergy balance equation one can write as delta E F 5 to 1 minus I 5 to 1, where delta E F 5 to 1 is equal to m E F 1 minus E F 5, and I 5 minus 1 is equal to T S equal to mt naught S1 minus S5, and that is the entropy at station 1 and station 5 respectively, minus H1 minus H5, that is enthalpy at station 1 and station 5 respectively upon TL. So, the exergy efficiency of the cycle, this can be defined as eta E exergy delta E F5 to 1 upon W, and it is equal to minus I 5 to 1, where the compressor work is the actual work and not the isentropic one. So, the value of delta E F5 to 1 is less than 0, since its flow exergy decreases at the exit, and in order to have the efficiency positive, we drop the minus sign for this delta E F5 to 1. Now, it is time to have another numerical problem. Now, here let us consider that a refrigerant R12 is using by the refrigerator, and the evaporator temperature is minus 15 degrees Celsius and condenser temperature is 40 degrees Celsius. The mass flow rate of the refrigerant is 0.1 kilogram per second. The surrounding temperature is 25 degrees Celsius. So, you need to calculate the flow exergy rates and exergy efficiency of the system. We have given some useful data in the tabulated form for different stages like 1, 2, 3, 4 and 5, and the entropy in kilojoule per kilogram Kelvin. Now, you see again the same aspect we have applied. If you see that enthalpy kilojoule per kilogram, and the stage 4 and stage 5, they are having the isenthalpic operation and they are having the enthalpy of 74.59 each. Apart from this, stage 1 is having the enthalpy of 181.2, and stage 2 and 3, they are having the enthalpy of 184.8 and 226.7 respectively. Similarly, if we talk about the pressure, which is represented in kilopascal. So, all the stages stage 1, 2, 3, 4 and 5, they are having 175, 150, 1200, 960 and 250 respectively. Now, if we see that the temperature profiling, that is temperature is represented in degrees Celsius. So, stage 1 is having the temperature of minus 15 degrees Celsius, stage 2 is having the temperature of minus 10, and stage 3 75, and stage 4 is having 40 degrees Celsius temperature, and stage 5 is having minus 6.25 degrees Celsius temperature. So let's solve this problem. Now the flow exergy rate difference for process 1 to 2. So delta E is equal to minus I 1 to 2, and that is T naught, and this is mt naught S2 minus S1 minus H2 minus S1 upon T naught. That is equation number 1. So we are having the values obtained from table, and if we substitute the value in this particular equation, we get minus 0.1 into 25 plus 273 into 0.734 minus 0.7086 minus 184.8 minus 181.2 divided by 25 plus 273. So delta E F from station 1 to 2 comes out to be minus 0.352 kilowatt. Now similarly, the flow exergy rate difference for the compressor, that is from 2 to 3. So delta E F from 2 to 3, that is as per the discussion 2 to 3. Now here, if we expand this mathematical relation, so it comes out to be H3 minus H2 minus T naught S3 minus S2. That is equation number 2. So if we substitute the values which is given in the table, so we have delta E F from 2 to 3, that is 0.1 into 226.7 minus 184.8 minus 25 plus 273 into 741 minus 0.7324. So it comes out to be EF 2 to 3, 3.93 kilowatt. Now for flow exergy rate difference for condenser, that is EF 3 to 4, is equal to minus I 3 to 4, and that is minus M T naught S4 S3 plus H3, and that is equation number 3. So if we substitute the values from the table, so it comes out to be EF 3 to 4, and that is minus 0.1 into 25 plus 273 multiplied by 0.741 minus 0.2718 plus 226.7 minus 74.59 divided by 40 plus 273.15. So delta EF 3 to 4 comes out to be minus 0.4 0.93 kilowatt. Now for flow exergy rate difference for expansion valve. So this is between this one. So delta EF 4 to 5 is equal to minus I 4 to 5, and that is minus M T naught S5 minus S4, and that is equation number 4. So if we substitute the value, then it comes out to be 0.1 into 25 plus 273.17 into 0.2867 minus 0.2718, and delta EF 4 to 5 is equal to minus 0.444 watt. So the flow exergy rate difference for evaporator can be written as delta EF 5 to 1, and that is T naught S1 minus S5 minus H1 minus H5 upon TL, and that is 0.1 25 plus 273.17 into 0.7086 minus 0.2867. All these values are given in the question itself. So 181.2 minus 74.59 divided by minus 15 plus 273.15. So delta EF from 5 to 1, it comes out to be minus 0.266 kilowatt. So the exergy efficiency for refrigeration cycle is given by exergy delta EF 5 to 1 W, and that is 0.266 upon 4.19. So this is 0.063. Now W can be found out as W is equal to M H3 minus H2, and that is 0.1 into 226.7 minus 184.8. So W is equal to 4.19, and that is the answer. So in this particular lecture we had discussed about the energy analysis and exergy analysis with reference to the vapor compression refrigeration cycle. So for convenience we have enlisted references, and if anyone wishes to go in detail about this vapor compression refrigeration cycle, they can utilize these references for their convenience. Thank you very much.